This, our country and all its people, could be in danger of nuclear attack in minutes by enemy missiles, in hours by enemy aircraft. Our cities, our farms, our factories. Prime target would be our air bases. With all our aircraft on the ground, our weapons of interception or retaliation not instantly available, we might face another and infinitely more costly Pearl Harbor. To avoid surprise disaster, some of our aircraft must always be in the sky or on the alert, carrying nuclear weapons. These weapons are always unarmed. They will be armed only following a decision by the President of the United States. Only these ready aircraft with nuclear weapons can form our first-line deterrent force in peacetime, our sure striking force in case of attack. We, the American people, understand and accept this necessity for our survival. But we want to know the facts about one question. Do we live in danger of nuclear explosion and radioactive fallout if one of these airplanes should crash, or one of these nuclear weapons accidentally drop? To give you the facts, the United States Air Force presents This bomber carries a nuclear weapon. It is a well-designed, carefully maintained, skillfully flown airplane. But airplanes, just like it, have crashed and burned. There was no nuclear explosion, no radioactive fallout. These are the facts. The bombardier watches over controls as safe as human ingenuity can make them to prevent accidental bomb release. But nuclear weapons have been dropped inadvertently. There was no nuclear explosion, no radioactive fallout. These are the facts. And specially instrumented aircraft verify these facts in a continuing nuclear safety program that tests our nuclear weapons under controlled conditions that simulate every conceivable hazard. Vital to this nuclear safety program is Air Force Special Weapons Center at Albuquerque, New Mexico. Here, in ultra-modern laboratory buildings, work scientists in and out of uniform. They work with the incredibly complex equations of nuclear physics, which derive from Einstein's famous relationship of mass to energy. These cryptic figures, programmed into lightning-fast computers, are the theoretical base upon which these scientists, together with those of the Atomic Energy Commission, can build nuclear weapon safety. By research, design development, and laboratory test, they ensure weapons not yet built against accidental nuclear explosion. They have been doing this successfully since 1945 in safety conferences with other Defense Department agencies and the Atomic Energy Commission. In 13 years, there have been a few accidents, but not one has resulted in nuclear explosion or radioactive fallout. These are the facts. What keeps our nuclear weapons safe? To understand why there has never been an accidental nuclear explosion, you must first know how these explosions can be produced, the general principles of nuclear explosions.
Any explosion is the result of a very rapid release of a great amount of energy. Conventional explosions result from the rearrangement of whole atoms in some explosive material. For example, in TNT, the rearrangement of whole atoms of hydrogen, carbon, nitrogen, and oxygen produces explosive force. On the other hand, nuclear explosions result from the rearrangement within each atom. This may be a joining together or fusion, as in an H-bomb, or the splitting apart or fission, as in an A-bomb. At present, an H-bomb explosion starts with fission, so the splitting of the nucleus of the atom is the basic principle of nuclear weapons. All matter is composed of one or more of the 100-odd elements. Of these, the atoms of the metals uranium and plutonium can be most readily fissioned to cause nuclear explosion. These elements are mildly radioactive. They emit short-range, low-penetration alpha particles while in their unfissioned state. These alpha particles do not have the harmful effects of the longer range and stronger gamma rays, which are given off by certain elements such as radium or by the products of nuclear fission. The atoms of uranium and plutonium are among the heaviest. Heavy because the nucleus of each atom contains large numbers of the fundamental particles called protons and neutrons. When a free neutron hits this nucleus, it splits into two parts, releasing more neutrons which may go on to split other nuclei. The resulting fission products become highly radioactive, emitting the long-range and dangerous gamma rays. The split nucleus weighs less than the whole one, and this difference in weight is released in the form of energy, nuclear energy. After fission, harmful gamma radiation. Before fission, innocuous alpha radiation. To build up a nuclear energy release, the fissionable material must be of a certain size, shape, or density. Then one of the neutrons escaping from a split atomic nucleus will, in turn, split another, and a chain reaction is set up. The mass is now releasing nuclear energy, but not quickly enough to cause a nuclear explosion. This condition is